close. Okay, so limits, continuity. Okay, so this is the first time that we start to enter the idea of calculus. So far, we've only been doing algebra stuff. Okay, so now we begin calculus. Yes, so exciting. Okay, so we're going to talk about limits. Limits. Okay, so check out this definition. Informally, a limit is a y value. Did you notice how I enunciated that part? It's a y value, which the function approaches as x approaches some value. Crystal clear? Oh, really? Okay. I didn't think you would really agree with that. Okay. So here's the notation. Has anybody seen this notation before? This is not new information? No. Oh, excellent. Approaches C is the limit. Okay. So I'm going to underline a word because it's super important. Approaches. Okay, so this is this idea of looking at the function from the left and to the right of whatever C value we're looking at and seeing what the function is approaching. Okay. All right, let's check this awesome, gnarly function out here. Okay, so we got this, that's definitely got to be some kind of a piecewise function, right? So, yeah, that's cool. Okay, so coming over here, the first question says the limit as x approaches -4. Okay, so looking at x being -4, what is the y value that the function is approaching? What is the y value? Give me a number. 1. Okay, so does everybody see how this is approaching 1 from the left and from the right? It's going to 1. Okay. Number 2. What is the limit as x approaches -1? 4. Is everybody okay with that?
Yes.
Yes, no, yes, no. Okay, at -1, from the left it's going up and going to this little hole right here. And from the right, it's going to the y value of 4. Good? Okay, number 3. What is the limit as x approaches 2? 1. Okay, so the y value right here where that hole is approaching 1. Stop me if you're not following this, please. Okay, moving on. The limit as x approaches 3. Okay, do you see how on both sides it's both going down? Okay, it's -infinity. Now, there are some mathematicians who would argue with this answer. Okay, infinity. What is infinity?
It's like idea.
Yeah, it's like an idea. I can't hand you an infinite number of pencils. So they're going to say, well, that doesn't exist. That's not a number. You have to give me a number. Okay, so if it's not -infinity, then what is it? It does not exist. Okay, so you can give either of these two answers on this. On the AP exam, they will accept both. Okay, so as long as in both directions it's going to the same place, it's going down to -infinity, that's okay. That -infinity is not finite and therefore does not exist. Okay there?
Those two lines don't meet somewhere.
Because, yep, the vertical, do you see that dotted line? Yeah. So that dotted line is representing a vertical asymptote. But, good question. Okay, number 5. At 5. Ooh. Okay, everybody okay with does not exist? Now that one you have to say does not exist. There's no alternative answer. Okay, because from the left side it's going to -1, but the right side is going to 2, and they're not going to the same place. Right? Do you guys remember that?
Yeah.
Okay, so if they're not going to the same place, it does not exist. Is that a new concept to anyone? Okay. Let me know if you're confused. Yes.
Question. So the one, let me see what number that was. I think it was number 2.
Uh-huh.
So why did you choose that one when you dots down?
Okay, good question. Okay, now I would say that the dot down there is the function value, not the limit. Okay, the limit is what the function is approaching from both sides. Okay, so you're kind of like zooming out a little bit and saying, okay, what's happening on the left side? What's happening on the right side? Are they going to the same place? Do you see the difference?
So even if there's not anything there?
Right, even if there's not anything there.
Okay.
Yes.
Okay. It's coming back to me.
Okay. Okay, so now 8. Now this is a different question. Now we're finding the function value. What is the function value at -4? 1. Okay, that one is pretty concrete. Okay, what about number 9? What is the function value at -1, Ren?
Oh wait, -1, sorry. 1.
1. Okay, that is now where the little dot is, and it exists exactly at 1. Is everybody okay with that? Okay, what is the function value at 2? Good, there's a hole. There's nothing there. It does not exist. Very good. What about at f of 3? Okay, also does not exist because there's a vertical asymptote there. There's no function value exactly at 3. Good. Okay, and what about at 5? 2. Oh, that was like everybody answered 2. Good. Does anybody have any questions on those? This is one of those things that is like super easy once you get it, but sometimes it's hard to get to the get part, get to the got part. You see what I'm saying? Is everybody to the got part? Got it? Huh? You're catching. Okay, so do you guys remember what one-sided limits are? Okay, so one-sided limits are from either the left or from the right. Okay, so this little notation with the minus means coming from the left. Okay, I don't know if you need to write that down or not, but maybe you remember that. And the plus means coming from the right. Okay, so looking at our function, what is the limit as x approaches 5 from the left? -1. And what about coming from the right? 2. Is anybody confused about that? Everybody remember left and right sides? Check it off the list. Done. Awesome. Okay, so the second part of this is talking about continuity. So anybody remember what a continuous function is? It does say it. Does anybody remember though? Okay, I'll read it for you. A continuous function is a function that you can draw without lifting your pencil. Okay, I think that is the most basic idea. If you can draw it without having to pick up your pencil, then it is continuous. Very simple. Okay, so.
What about the holes that you're drawing? You can go around the circle and back.
Ooh, I don't know. I would probably draw it and like pick up my pencil and like draw a circle, and then pick it up again.
Draw circle.
You just had to second guess it. Okay, let's assume when we draw a hole, we lift up our pencil. Okay, so give me the 3 types of discontinuities, types that you have to lift up your pencil for. Holes, vertical asymptotes, jumps. Ooh, it is up there. It's even underlined. Holes, vertical asymptotes, and jumps. Okay. So, 13 says, list the x values of the discontinuities of the function that is graphed above. Okay, so where do you see a hole?
2.
2.
-1.
-1. Any vertical asymptotes? At 3. And any jumps? At 5. Okay, so we have discontinuities at x equals -1, right? +2. There's a vertical asymptote at 3, and then a jump at 5. Easy peasy? Okay, so the second part of discontinuities is describing the types. There's two types of discontinuities. What are the two types? Removable and non-removable. Okay, so what is a removable discontinuity? The whole.
What about a hole that doesn't have? Yes.
Still removable.
Okay.
Yep.
No matter what a hole.
Yep, whole of any kind. It's removable. Okay, non-removable is jumps and vertical. So like you can literally see the big jump or the break apart. Ooh, good word, break apart. Okay. Number 14 says, which of the discontinuities from 13 are removable? Okay, so which ones have holes? Ooh, yeah, that's a break apart. So just -1 and 2. Okay, 5 is a jump, so that's a non-removable. Okay, so clear on continuity. Okay. All right, so now they jump into finding limits. Okay, so the first method of finding limits is by using direct substitution. So guess what we're going to do for question number 15? Directly substitute the limit value into the function. Okay, so what's my limit value I'm going to plug into number 15? 3. Okay, so all you do is you simply plug 3 into the x and simplify. So would everybody agree that 3 times 9 plus 2 is 29?
Yes.
Okay. That's simple, right? Okay, what about 16? What would you do there? Plug in 1. Okay, yeah. 1 squared plus 1 over 1 plus 1. That makes 2 over 2, which is 1. Okay. Good there? What's that? The limit. The limit of the function. So the part up here we did graphically. We found limits graphically by looking at the graph. Okay, to do it algebraically, so let's just say they give me the function and ask for the limit. Okay, I can do it by direct substitution. So all you do is directly substitute the number in, and it will output your limit value.
But isn't that telling the limit is that x2?
Yeah.
So what is the output value?
The output value is the limit.
X goes to that says X approaches 3. That's not the limit.
Okay. Sorry.
Is that what you asked for?
Yeah, thank you.
Okay. Thanks for answering her question. Okay, now things get a little more interesting when we start dealing with piecewise functions. Okay, so remember, in order for a limit to exist, it has to be the same value, approaching the same value from the left and from the right. Okay, so if we're looking at this number 17, we basically have values that are on the left of 1, which is going to be this linear function. And then we have values that are on the right of 1, which is this upside down parabola function. Okay, so how are we going to figure out what the limit as x approaches 1 is? The top one? Yeah, we got to test both of them. Okay, so the idea here is, are these two functions coming together at the exact same point when the x value is 1? Are they going to touch? Okay, so all we have to do is plug it in. We're going to do a direct substitution, and we're going to plug it into both equations. Okay, so kind of over on the side, if I go 4 minus 1, that would equal 3. Okay, and if I do, let's see, 4 times 1 minus 1 squared, that's the same as 4 minus 1, which is 3. Okay, so that means coming from the left, see how I'm saying the left? Because those are the values less than 1. It's approaching 3. and coming from the right, it's also approaching 3, so therefore the limit value is 3. Okay.
Yeah, the answer calculates.
So what about 18? What are we going to do for 18?
The same thing.
Sure, the same thing, right? Because again, it's asking for the x value of 1, which is where this piece divides itself. Okay, so we're going to plug 1 into both pieces. So we've got 3 times 1 minus 1 cubed, so that would be 3 minus 1, 2. And 2 times 1 squared minus 1, which is 2 minus 1, which is 1. Okay, so in this case, the left side is approaching 2, the right side is approaching 1, so therefore, the limit does not exist. They are not approaching the same value from both sides. Okay, interesting question, number 19. Okay, so it says we're going to use the g function, so this one right here, and this time we're going to find the limit as x approaches a negative 1. How do we do this question? Why the top equation? Yeah, right? Okay, the value of negative 1 is less than 1, so I only have to plug it into the top piece. And since the top piece is continuous, I know it's just going to approach that corresponding y value. Okay, so I'm just going to go 3 times negative 1 minus, negative 1 cubed. That's a lot of negatives. So that would be like the same as negative 3 minus, no, plus, right? Plus 1 minus a negative. Yeah. So that would be negative 2. Okay. Good there? Okay. Oh my gosh. That printed terribly. Does your guys' look like mine?
Yeah.
It does? Okay.
So bad.
It's not what it's supposed to say. Okay, so this is a greatest integer function. So what it's missing right here is these like, have you seen these brackets before?
Oh yeah. Oh yeah, that just has a.
Ours has that.
Oh,
Ours
yours has that?
Double line.
Oh, okay.
Just 2
That's
lines,
at
no
least closer
brackets.
than what mine has.
You want to stack the little
Um,
brackets on top?
You know, I don't think it's too far off, but maybe, probably, yeah.
So it's like brackets.
I think that that's really close. Yeah, it's kind of like more like bracketies. And then it says what does yours say? The greatest. The greatest integer. Weird. The greatest integer less than or equal to. Okay. So just quickly understanding the greatest integer function. So let's say I say if my input is 2.1. What is the greatest integer that is less than that number? 2. Okay, so I input 2.1, my corresponding y is 2. Is still 2. Okay, what about 2.8? Rounds down to 2. Okay, so it's slightly different than rounding. So if I say 2.999999999,
2.
That's still 2. Okay, so that's why this looks like a, anybody want to describe that? Staircase. They call it a step function for obvious reasons. Mathematicians are not extremely creative, so very literal. Okay, so that's a step. Okay, so they ask us for the limit as x approaches 1/2. Okay, so if you look over here, 1/2 is right here. What is the corresponding y value there?
0.
0. Okay, which you could input that, right? 1/2 would round down to 0.
You always round down?
You always round down on greatest integer. Yep.
Yeah.
Okay, what about at 1? Okay, now that's the function value at 1. I agree with the function value, but what's the limit? What's happening at 1? Yeah, right? Okay, from the left it's going to 0, but from the right it's going to 1. So what's the limit? Does not exist. Is that it? That's it. Pretty easy?
I don't think we can do it.
You can do it. So easy. Okay, so you guys have 1 through 30 for problems tonight. 1 through 30. Okay, so a lot of these first problems are those quick, simple graphing ones you can probably finish before you even leave class.